Alright, this video is to help us understand how to use binomial probabilities, or essentially how to use the binomial theorem, or the terms of the binomial theorem, to help us with probability scenarios. Let's consider the question that we have on the screen here. The probability of rolling a 5 on a fair 6-sided dice is 1/6. If you roll a single dice 10 times in a row, what's the probability of rolling a 5 7 of those 10 times? Now, that might seem like a simple enough question of just saying, well, hey, if we're going to roll that 5, then we're going to roll it 1/6. Sorry, let me switch colors here. We're going to have a 1/6 for the first roll, because we need to roll that 5, and there's a 1/6 chance of rolling it. But now if we're going to do that 7 times, we would want to multiply by 1/6, and 1/6, and 1/6, right? And we want to do that 7 times over. Well, the problem comes in that by doing those in order, and then even remembering to multiply, well, hey, that's only 7 of the rolls. That means that 5/6 of the time I need to roll a non-5, right? Because that can roll something else, those other 3 rolls. I do have to roll 10 full rolls. The problem is that also assumes the order. That assumes that I rolled 5 7 times in a row, and then I missed. I rolled something else 3 times in a row. And we're forgetting about those extra orders. If it helps, think about doing that. Think about doing that exact same thing, but what if we only consider 2 rolls? What if I roll a dice twice? What are all the ways that can kind of happen? Well, I could either roll a 5, right, and another 5, or I could roll a 5 and a non-5, or I could roll a non-5 twice. The problem is if we multiply those all out, that's 1/36, and this is 25/36, and this is only 5/36. If you add all those up, 1 plus 5 and 25, that's only 31 out of the 36 possible things that can happen. What happened to the other 5? And again, the problem comes in that middle case. We've assumed the order. We've assumed that we rolled a 5 and then we didn't roll a 5. What about switching those 2 things around? Essentially, this middle case needs to happen twice, so that when you add them all up, right, because that one can happen in 2 different ways, then we'll end up with a full 36 out of 36. And remember that any probability should happen, right? Any probability that's going to happen correctly should happen, or add up to happening 100%, right, of the time. Let me clear this all out of here. And let's go back to our question of, well, what if then we roll that dice? How often, or how can we get it to happen, probability of it happening, 7 out of the 10 times? And what it goes to is this binomial probability up top here, right, our formula on the top. We need to consider NCR, using those combinations of all of the ways in which this can happen. It is very true that, yes, we are going to take 1/6, and we're going to roll that 1/6. We're going to get a 5 on our dice, and we want to get that 5 7 times. We also are going to roll 3 extra times, and the probability on those, we don't want the 5. We want something other than the 5. So that's going to be 5 out of 6. But what we have to consider is, in the beginning, on those 10 rolls, we want to get our successes. We want to have exactly 7 successes, and we can do that in 10 combined 7 different ways. Okay? If we take a second and we compute that number, right, we go onto our calculator, math, over to probability, and we compute that number. Again, we wanted to put our 10 in first here, so we needed to say 10 combined 7 different ways. We can do that 120 different ways. So we need to take 120 times 1/6 to the 7th times 5/6 to the third. And if we actually compute that, so we're going to multiply that number that we just got by 1/6 to the 7th. And then we're going to multiply that again by 5/6 to the third. And if we compute that number, it should be, and again, e to the -4, so let's move our decimal 4 units to the left, basically 0.123, and if we round it off, 25, there's the probability, again, of rolling 7 times out of 10 rolls. And again, it should be fairly unlikely. Rolling a 5 once is only a 1/6 probability. Rolling it more than half the times, rolling it 7 out of 10 times, should be pretty rare. Let's apply that same idea to a real-world scenario, such as Joe Mauer in Major League Baseball here. In 2006, Joe averaged a .347 batting average, which means that about 1/3 of the time, Joe would get a hit, maybe a little bit more than 1/3 of the time in any given at-bat. What we want to know is, what are his chances of going 3 for 4, having a pretty good day? Well, we can use that binomial theorem. Again, the first thing we want to think about is, well, to go 3 for 4 doesn't mean he's going to get 3 hits and then 1 out. We first need to find the possible number of ways, give the possible hits versus outs for Mauer's at-bats if he's going to go 3 for 4. Well, he could have 3 hits and then an out, but really that out could be positioned in any one of his at-bats. Technically, there are 4 different ways in which Joe Mauer can go 3 for 4. So what we need to do is set up that binomial theorem, set that up, and figure out how we can do that. Well, the first thing we need to consider then is the number of ways. And again, those 4 different ways, positioning that out either in the first, second, third, or fourth at-bat, essentially is going 4, choose 3. We're going to get 3 hits out of our 4 at-bats. Then we also need to multiply that by, again, the likelihood that he gets a hit. .347 is, again, the probability that any one at-bat is a hit. So if we do that 3 times over and then get a non-hit, well, if there's a 347 chance of him getting a hit, then subtract that from 1, there's a 0.653% chance, or probability, I guess, not percent chance, 65.3% chance that he's not going to get a hit. Well, that needs to happen 1 time. So we'll multiply those probabilities and multiply that by the number of ways in which that can happen, and basically find out that there is about a 10, almost 11% chance, a 0.1091 probability that he has a 3 for 4 day. We can also apply that to larger situations. Well, what's the probability then that he gets 2 or fewer hits, that his hits end up less than 2? And actually not even 2 or fewer, just fewer than 2. What's the probability that he either goes 1 for 4 or even 0 for 4 on any given day? Being a net batter who gets essentially a hit 1/3 of the time, 1 out of 4 or 0 out of 4 should be fairly unlikely. Well, we'll set those up. Again, 4C1 and 4C0. A hit once with 3 outs, or a hit none of the times, 0 out of 4, with 4 outs. Compute those 2 probabilities and add them up. And really, even for the best batter in the league at that point, 347 hitter, there is more than a 50% chance that he's going to go 0 for 4 or 1 for 4 on any given day. Again, that's the hard part about baseball, I guess. I hope that helps you understand the binomial theorem a little bit and independent probabilities. Again, any given at-bat is independent of a previous at-bat. So therefore, that's why we can just multiply the probability of something happening by the probability of something not happening and be comfortable with, we don't have to worry about any sort of intersection. It can't both happen, and you can't get both a hit and not a hit in the same at-bat. If you have any questions about independent probabilities or the binomial theorem, make sure you talk to your teacher. And otherwise, have a great day and happy counting.